Hi everybody, welcome to my video blog. In this episode, we'll take a look at my new curve tracer, a really big VFET, sit modeling software, using Excel to model sits, and an Ironamp update. Okay, well, I'm pretty excited about this new piece of lab equipment. This is a Tektronix 577 curve tracer. And I never thought that I would own one of these, but one came along at the right price, and it's in really good shape. And it came from a community college, and it looks like the students hardly used it at all. And so I'm really excited to have this in the lab, and I'm really enjoying using it. And it came along at a great time because I just found some of these. I found these Tokin 2SK180 VFETs on a Chinese website, and I was a little concerned about what I was going to get, but I rolled the dice and bought a few, and I just got them in the mail. And check this out. That looks like a real VFET transistor. So great. Now, what's so great about these things? Well, look, it's huge. It's twice as big as a 2SK82. This is a 300 watt device. And what that means is that we can build a really big single-ended amplifier with this. All right, here we are at the computer, and I've got my screen resolution lowered quite a bit so that you can see this on video. And we're here to take a look at my interactive SIT modeling software. Recently, a fellow DIYer named Juan Antonio sent me an email. He has been experimenting with the 2SK180, and he's been making some curves and working on a model. And he wrote to me and asked a couple questions about how to use the software. So I thought I would take a minute and show you how it works. It's just a web application, so it will run just about anywhere. It runs best in the Chrome browser. It also works in Safari. It will work in Internet Explorer, but Internet Explorer doesn't support all of the features and controls. So it works best in Chrome and Safari. You can see there's not a lot to it. It's very plain. It's just something that I developed for myself while I was working on a mathematical model for static induction transistors. I needed something that would allow me to change parameters and watch a graph update in real time so that I could understand what the parameters were doing. And indeed, you can see that if I change the values, that the graph updates in real time. And that's fun, but it becomes useful when you load an image into the background here, and then change the parameters in order to line up these traces with the photograph. And that's how you build a model interactively. So we're going to work on a model for the 2SK180. And so the first thing I'll do is change the name on the model. And the next thing we need to do is adjust the scale, because the photograph I'm going to use is 100 volts max in steps of 10, and 2 amps on the y-axis in steps of 1 is fine, and the gate voltages start at 0 and end at -14 in steps of 2. So now I need to import my photo into the background, and I'll show you. This is a photograph that I took of my curve tracer screen, and we'll import this, but we need to fix it up a little bit first. And so I'm going to edit this in Microsoft Paint. We just want the plot area of this photo. We don't want all this extra stuff. So we use the select tool, and we'll just select the plot area and then crop it, and then just resave it. Okay, and now it's ready to import. Just go down to choose file and select our image, and there it is. You'll notice that it has lightened the photo a little bit. That's so that you can see the traces better against the background, and you can adjust the lightness of the background by just changing this opacity value here. Okay, so it's time to start adjusting some parameters and trying to get these curves to line up. One thing I know that I'll need to do right away is I know that this move figure is going to be bigger. You can see in the photo that the move is increasing quite a bit as the drain voltage increases, and so I'm just going to start there. I'm going to crank this up to maybe 10 or something like that and see where we are. Okay, and it looks like we need to keep going, so okay, I think I might be getting close with that. So I mean, you can see that the drain resistance isn't quite right, and so we need to start adjusting some of these other parameters. So take the K up a little bit there. This is the N parameter. This is the sort of triode pentode shape control that I built into the model. It just helped to make things fit a little better, and you can see we're kind of headed in the right direction here. straighten those back up a little bit. Okay, you can see that you get the idea. This is really pretty good, and that's about 3 minutes worth of work. We could continue on with this for another half hour or so and get it even closer, but I don't want to bore you to death with that. That's how you build an SIT model with the trial and error method interactively. And to turn this into a SPICE model, you would just enter the capacitances if you know them. If you don't, that's fine, just leave them out. And this is the text for the model. You just copy and paste this text into your model, and that's your SPICE model. It tells you the range for the model, and also if you're using multisim, you will want to comment out this line by adding an asterisk at the beginning and uncommenting out this line here. I've used this model in multisim, I've used it in LT SPICE, I've used it in other generic versions of SPICE, and I've been able to get it to work in just about anything. So there you go. That's the interactive SIT modeling app, and that's the trial and error method. Now I'm going to show you a way that you can use Microsoft Excel to figure out these model parameters. So stay tuned. Now we're going to take a look at how to use Microsoft Excel and the Solver add-in to determine values for the SIT model parameters. And the first step is to extract some X and Y data from our curve tracer photo, and we do that with an application called Graph Grabber. There are other applications out there that do this, but this one's pretty good and it's free. And the first step is to import our image, and it's going to zoom out so that we can get the whole thing in frame here. Alright, so what we need to do now is we need to tell the application how to scale this photo. So I'm going to set the x-axis, and the min is 0 and the max is 100 volts. And now I'm going to set the y-axis, and the min is 0 and our max is 2 amps. You could go crazy and adjust your photograph for skew and all kinds of things like that, but I'm not going to get too crazy about that right now. Now that we've got our photograph loaded and our scale set, it's time to start adding some data, and we do that by clicking on Add Data Series. And now I'm just going to click along this trace and acquire some values. So I'm going to start down here near 0, and I'm just going to start clicking values, trying to stay in the middle of the trace as much as possible. Okay, let's finish that. And now let's add another data series. And now we just do the same thing, starting near 0 here. It's nice to have lots of data points for this. It helps you get better results. Okay. And now I just repeat those steps for the remainder of these traces. When we're all done, we want to export this as a CSV file, comma separated values. And let's just call it 2SK180 and save it. And now we've got some numerical data that we can use for our analysis. Okay, so now we have some numerical data, and we're ready to do some curve fitting using Microsoft Excel and the solver add-in. I'd like to thank Jack in New Jersey from techdiy.com for posting information on how to do this for vacuum tubes, and all I've done is just extend the concept to SITs. This is what the data file looks like from GraphGrabber, and you can see each series is just XY plot data for one of those traces. Now I've taken that file and added some columns, and now it looks like this. I've added a column for the model, so this is a predicted value column. This is the actual drain current, and this is the predicted drain current. This column is chi-squared column is it's the square of the difference between the predicted and actual value, and then I've summed up all of those chi-squared values here for our total error, and we'll use that to optimize our fit. I've also added a graph over here so that you get kind of an visual indication of how good the fit is. The actual data is represented by these bubbles, and the predicted values are represented by these solid lines. And presently I just have some arbitrary values, arbitrary starting values entered. So our fit obviously is not very good at the moment. To use Solver, you'll find it in the data ribbon, and Solver is not installed by default in Excel, so you will need to install it. Once you've done that, you just click on Solver. And the way Solver works is you set an objective, in this case our chi-square sum, and we want to minimize that. And we do that by changing these values. In this case, these are the model parameters. And I've set one constraint here. I've said I want this exponent to be greater than or equal to 1.5, which is the 3/2 power law. And we're using the GRG nonlinear solving method, and I haven't set any options there. So let's just click solve, and the solver iterates through and finds a solution that it likes, and you can see that it has reduced that error, and this is what the result looks like, and that looks pretty good. And so that's how you use Microsoft Excel and the solver add-in to do some curve fitting and find those model parameters. I should mention that when you're fitting curves and working on these models, that if you need to prioritize, then you want the model to, you want the curves to fit best where you're going to use the model. So if your circuit is going to, the operating point for your circuit is going to be 50 volts and 1 amp, then you want the model to fit closest in that region, and maybe it doesn't matter so much what it looks like at 0 gate voltage or whatever. But there you go. I hope that that was useful or interesting or entertaining, and stay tuned for an Ironamp update. Okay, I know I promised an Ironamp update, and here it is. That's one channel of Ironamp. It's real. It will be ready soon. Right now I'm just waiting on some new input transformers from Edcore. There's the power supply circuit board and some of the components. And so there it is. That's Ironamp. Before I sign off, I'd just like to say thanks to all my friends at DIY Audio. Thanks to Nelson Pass. I'm just going to keep thanking him every chance I get. And just keep having fun, everybody, and go build something.